Good morning, everyone. I'm Jiang Dai from Taipei Multimedia team. My nickname in IRC is C Dai. Today, I would like to introduce a new project, FoxEye, and my colleague Kaku will show live demos. So, what is Project FoxEye? Let's see a diagram. A fox is standing on the shoulder of giants. The concept is to leverage modern computer vision and image processing technology. So by providing a media stream track with web workers and providing a web image library and offline media context, we can cover most of the case of image processing. The blue part is the original web API. The top of diagram is for video, media stream API, and the right button is HTML image element. We will have a new library, web image. I will explain it later. It takes image bitmap as input and output arguments. So the image element can use the library. The next question will be, how does media stream track use web image? So by adding some functions into media stream track, we can associate media stream track with web worker. Then the web worker can use web image as a library. The monitor is for the case that worker doesn't have to process the frame on time. The processor is for the case that the image frame should be delivered in real time. Also, we can say the difference is, could we modify output frame in the worker or not? It means the worker could not modify output frame. So what is web image? It's a built-in library for some performance critical case and hardware accelerator case. Also, we will provide some OpenCV SM.js, something like that. Because some SM.js version of computer vision algorithm may run poorly on P2G. Also, in hardware accelerator case, like face detection in P2G, a lot of chipset vendors provide their own face detector in their camera. In that case, we need web image. So let's see a diagram. If the feature is not performance issue, we will use SM.js version, the pink block. But if the feature have hardware accelerator version, it goes web image way. For example, face detection module in P2G camera. If the feature in SM.js run poorly in P2G, in that case, we will maybe go web image way. You can also take the SM.js of OpenCV part as a part of web image. This is what the Drive API will look like. We will add 4 functions into media stream track to associate with workers. The top part. And add a new event handler into worker scope. We will add a video process. Also, a video process event includes check ID, playback time, input, output frames, and parameters. That will be a new event, like check ID, playback time. And we will use image bitmap as input frame and output frame. Also, we can accept the parameter. Let's look at the sample code. This is a main JavaScript file. Start from get user media to get the media stream, and get the media stream track. Then add a worker as a monitor. I think we will change to new video worker. We will add a worker as a monitor. And the callback of my worker on message will show the recognized text. So we will create a new worker called text recognition. We will recognize the frame from camera, and once it recognizes any text, it will post message to the main JavaScript file. So you will get the event the recognized test from the test declaration.js. So you will get the callback function will show the data. In the worker side, create a test detector from web image in the event handler. Get the input frame from the event and pass it to the test detector to find the test and recognize the test. Then post the message to the main JavaScript file. Actually, we can compile tons of existing native image processing engine to SM.js and run those engine in the worker. So we can create a test detector, or we can use ASM.js to create some image processing engine. And then we will get the event and get the input frame. We can call a library to processing the frame. And you will get the result and post the result to the main JavaScript file. So I will let Kaku show some lab demo.
Hi everyone, my name is Kaku. So you might have some brief idea about what FoxEye is going to do. And now I'm going to show you some demonstrations. Although the project FoxEye is still in the proposing stage, we already have some prototypings and have some demonstrations. And now I'm going to show you two demonstrations. One is segmentation, or you can call it background removal. Or the other one is face detection. Okay. So this one is a web application that has the segmentation functionality, and this interface is need you to drop an image that you want to do segmentation into it. So I have prepared several one, and let's try one. For example, we would like to segment out our Firefox logo. This interface is designed to be interactive, so users need to tell the system some hints where the main object is. So please drag a rectangle around the main object. For example, like this. Sorry. Let me restart it again. How to switch the full screen? No, 没有用。那个 Option Command F 没有用。哦。
对不起 ，Control Command F。
哦。哦，有了。Sorry。Again. Okay, just like this. The system will mark the background part as red, just as you saw here, and the foreground part, which is smartly segmented out, will remain its original color. Okay, and next demonstration is about face detection. This application uses the get user media to access the local camera, and it will do face detection frame by frame. Just like this. Yeah. So the performance is good enough. It's about 6 frames per second on the Mac, and it can run about 20 frames per second on the phone device. Okay.
We use SF.js.
So here
is an example of the code. You chose the code for those two demos.
And I show code.
Yeah. Okay. In the next slide, I will show you the code. Okay. And here is the front demonstration. You can see.
So you're taking OpenCV as something.
Yeah.
And compiling it.
Yeah. Okay.
What I do. It's very. How do you measure the frames per second?
How do I measure it?
It's really good. Oh, it's fine. It doesn't work upside down.
Oh, yeah, doesn't work. Yeah. 这是个问题。
测量 PS 是
Maybe screw up.
就是啊，你是在哪地方测量？在 JS 还是？
对啊，JS，跟这个问题有什么问题？
Yeah.
应该是做一个 frame 要几秒钟，要几个 millisecond 再出现。那我觉得他忘了这个问题。
Yes, we should fall back.
So your question is how do I measure the frame per second? So I just measured how long it will take to process one frame, to do the detection from access the raw data and finally get the fake square faces. And so I know how long will it take to process one frame, then I know the FPS. Okay. So everyone saw the demonstration, and the demonstration can be accessed through this website. And the source code are all hosted on the GitHub. So do you guys want to show the source code now?
So do we need a special deal of Firefox?
Yes, I will. There's two versions. One use the original, the old released Firefox is okay, but another one need a new API called the image bitmap, which is not already in the Firefox now. Yeah. Okay. Let me go through the slides, and maybe if we have time, we can go through the code. Okay. And these two demonstrations only use the HTML5 plus pure JavaScript code only, and we do not use the WebGL to optimize it. Yeah, of course, no native code. So what do we use in the previous demos, and what have we done for the project FoxEye now? There are two parts. The first one is called the OpenCV.js, and the other one is we extended the Gecko with image bitmap double prime. So I will explain why it's double prime later. And let's start from the OpenCV.js first. So OpenCV, maybe someone here knows this library, but I will give you a brief introduction. It's an open source library focusing on the computer vision. And it supports lots of popular platforms from Windows, OS X, Linux, Android to iOS. Its code base is written in C++ code. but it provides three kinds of interfaces, written in C++, JavaScript, and Python. So we think that OpenCV is very popular for image processing and computer vision, and it's not only in the prototyping stage, but also in very real-world products. So if we can leverage on this powerful library, and if we cross-compile it to the web platform, it will be very useful. So that's what we do, the OpenCV.js. The OpenCV.js uses the same code base as OpenCV does, but it is cross-compiled via the encryption into JavaScript, especially it is into the ASM.js. So with JavaScript code, OpenCV.js supports web platforms. But actually, in practice, it only works on Firefox OS. Firefox now. Other web browsers doesn't support ASM.js so well now. So in short, how can you compile the OpenCV.js? It's very easy. You just need to download the OpenCV source C++ code base and put it into the encryption, and then encryption will give you the ASM.js version. But actually, there are some tricky parts inside. You need to do some configuration on the code base of OpenCV. And the OpenCV.js project is now maintained in this GitHub. In this GitHub, there is a step-by-step documentation to guide you how to compile the OpenCV.js. So if we have time, we can go through the wiki later. And let's talking about the others about OpenCV.js. And first is the performance. Here we test the OpenCV.js performance with a benchmark which contains around 2,000 performance test cases. So now, in current status, about 55% of the test cases is run in about 55% is good enough. It runs in no more than 2 times of the native performance. And if you are interested in the performance issue of OpenCV.js, you can follow these 4 bugs in Bugzilla. We summarized several patterns of obvious performance drops in these 4 bugs, and the Inscription and the ASM.js team have some insightful comments on these 4 bugs. So in the future, the performance will get better, and there is already a known issue in the Inscription is about the floating point to non-floating point conversion, and that known issue caused lots performance drop in this bar. And there is also another ongoing project called SIMD.js, which also will help a lot in the performance part. Okay, so that's all about OpenCV.js.
So just a quick question: how big is the resulting JavaScript file? How big is it?
How big is it? Okay, the segmentation demo. The JavaScript file is about 1 mega. Okay. And the basic declaration file is about 700 KB.
Okay.
Yeah, it's not so. Yeah.
You don't compile the entire function, just compile encryption to compile the recognition part, or
Oh, okay.
Yeah, I thought you compiled the entire OpenCV library.
Yeah, but the OpenCV.js contains whole parts of the OpenCV. But for each demonstration or for each application, you don't need to use all of them. So the runtime JavaScript file could be small.
So how big is the entire OpenStreetJS?
I don't know.
Because I tried to download the binary of, I'm not sure it's binary or source code. It's very large, like 90 megabytes.
Each source code contains some performance tests and samples, testings, documentation.
Because usually coding in JavaScript will double or even 10 times the code in C++. Yes. We are all wondering how big it will be.
I can check the data and tell you guys. Okay. So, any questions about OpenCV.js now? No. Okay. So let's go to next. I will introduce how we extend the Gecko with the image BMap double prime. So if you want to write a web image processing web application, here is the skeleton of such kind of application. So first of all, you need an HTML image element as the container of your source image. So to access its raw data, you must need to draw the image into a canvas element. And then you can use the getImageData method to get a JavaScript type array which contains the raw image. So now you have a JavaScript type array which you can process, but you might want to process it via pure JavaScript code, which is too slow. So we assume that you want to use ASM.js to process the raw data. Okay. So that you can use OpenCV.js. But there is a problem is that ASM.js runtime does not ASM.js runtime does not know external memories. It only knows its runtime heap. So you need to copy this JavaScript type array into the ASM.js runtime. So there is a extra copy operation here. So then after some creative processing, you might want to show the result on another canvas. So you need to put the raw data by put image data into another canvas and show the result. So the skeleton here contains several redundant steps, and also the performance is very bad. You can see the performance data here. The performance data is measured on the frame device, and the image resolution is 640 cross 480, and the color format is RGBA. So several questions raised. The first one is, can we access the raw data directly without go through a unnecessary canvas element? And the second question is, can we skip this copy operation? Can we make the ASM.js runtime be aware of the external memory? And the third one is about this method. This method looks very terrible. It takes 150 milliseconds to process one frame. So for the first question, can we skip this canvas element? Yes, the answer is yes. And we leverage the new proposed web API called image BMap. The image BMap is originally designed as an opaque interface to its underlying image data. Okay. So we extended the image BMap with an array buffer. And this array buffer could be the interface to its underlying raw data and export the underlying raw data to the JavaScript developers. And now JavaScript developers could set the attached array buffer to a typed array, and the so the flow can go following the original pipeline. And this is the first step. We skip the canvas element here. And next, we want to avoid this copy operation. So the real question is, can we make the ASM.js runtime knows external memories? But to the spec now and to our limited knowledge, the answer is no. So what can we do? We can turn corner. If ASM.js does not know external memories, but we could know where is the runtime heap is, where is the ASM.js runtime heap is. So we bind the already created ASM.js heap into the create image bmap method, so that the image bmap use the binded external buffer as is on buffer, and write the raw data of HTML image element or HTML video element into this buffer directly, so we can avoid the extra copy operation. And also by this way, we can also solve the third question here about the put image data method, which takes very long time to process one frame. The draw image method do the same thing, but with much better performance. Okay, so the previous, so this framework we called the image bmap double prime because we do 2 types of extensions about the original image bmap specifications. So next slide is almost the same with the previous one, but this slide is talking about the video processing scenario. And if you want to do video processing, if you use the canvas-based framework, the performance is about 50 frames per second on the frame device, and the measuring condition is the same with the previous one. And this data is without the processing time. But if you can use the image double prime based framework, the performance will get better to about 24 frames per second. Okay. So here is the image bmap double prime interface we would like to propose now. And except to the original width and the height properties of the image bmap, we add several properties which is going to support what we want to do. And the first one is channels stride format. This is used to describe the variety of underlying image data. There might be some different kind of color format, and they may contain stripes. And this tree is array buffer data, and the offset of the array buffer and the length of the array buffer, which is used to export the underlying image data to the JavaScript side. And about the image bmap factory, the original only contains the first 2 methods, which you give them, for example, HTML image element, and tell the factory which part you want to create as an image bmap. And now we extend these 2 methods with 3 extra parameters, which is array buffer and the offset and length, to describe where is the external memory is. Okay, so we summarized several drawbacks here about the canvas-based framework. Except the performance issues we described in the previous slides, there are 4 extra drawbacks. The first one is that the canvas-based framework use polling mechanism, which means that you cannot guarantee frame-by-frame processing. So this will be a vital issue about if you want to do the video processing. And the second one is in the canvas-based framework, it uses image data as the interface to access the raw image data. But image data is limited to RGBA color format only. And this is why we choose image BMap instead of image data, because the image BMap specification doesn't limit its color format. So we might export much more kind of color formats. For example, YUV. YUV is very useful if you want to do some processing. And Canvas 2D context now is limited to can only be used in the main thread. So there is no way that you can, for example, create a worker and do some processing work there and communicate with the main thread. You must block the main thread if your process time is long. And the final one is that in the current Web API and the current framework, there is no way to do the processing quicker than real time. Everything is stick to the real time processing. So we want to propose a new Web API called offline media context, which supports developers to process their data quicker than real time. For example, if you want to recode the video, then you don't need to go through the video in real time. You can do much quicker than real time. Okay. So that's all about what we have done for the FoxEye project. And Sita will go through the slides later about some scenarios.
So this is the current status. The first one is the meta bug is bug 11000203 is for the FoxEye project, and we will start from the 4 bugs. The first one is about hook video worker with media track. The next one is for OpenCV SMWS and P2G performance. And also the third one is image BMap implementation. And the last one is offline media context. And the offline media context we'll do later. So that's a use case. You can use the FoxEye to in the facing or AR camera panorama, fisheye camera, and comic effect, some filter effect. Also, if we have camera Halo 3, we can use like smile, snapshot, gesture, HDR, video stabilization. And also, you can use FoxEye to do some video editor. And also some photo editor. Another part is object recognition part. So we can use FoxEye to do some shopping assistant like Amazon Firefly and face detection recognition, also text recognition, and text selection image, intent image selection, and translation like Lego or Wallace. Also dual camera, we can support dual camera in the future. So this is a slide for how FoxEye can do in real world. Content and context awareness web is provide